Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So today we're doing another awesome video. Today, what are we doing today? Today we are doing the covalent bonding worksheet number 2. And really and truly, before you actually start this video and continue on, you're going to make sure that you do a few things here. Number one, you're going to make sure that you watch my previous video, that is covalent bonding worksheet number 1. Within that video, I go over the valence electrons that are on the periodic table and the electronegativity of the most electronegative element, as well as I cover this worksheet that I have designed, covalent bonding handout number 2. There's a top section and there is a bottom section to that. We'll be following the rules within this. If you want to get further information on this, then you should certainly go to my YouTube channel and my Honors Chemistry Unit 6, the bonding collection. Look in that video series, in that playlist, and find bonding number 28, molecular geometry. That will give you this whole molecular geometry, bond angle, polarity, axe, as well as this video here. It's in Honors Chemistry 6. It's in the same playlist of the bonding collection, but bonding video number 11, the Lewis dot structure rules. And I go over those specific rules one by one. So I highly recommend that you have done those two things before actually starting this video, because that is assumed to be prior knowledge. So without further ado, we're going to continue on. By the way, I am the Crazy Hat Chemist. That's why you're watching me, because this is the place where you get the good chemistry knowledge. I am the Crazy Hat Chemist. All right, fantastic. So here we go. Now we're going to zoom in onto this worksheet here so that we have more information here as large as possible. That's our goal here. All right, fantastic. I think we're there. Yep. All right. All right. So this methane, CH4, there's one carbon atom in this, and valence electrons is 4 and a carbon. And then there are 4 hydrogens, and the valence electrons in a hydrogen is 1. I'm going to add up those. That's 1 times 4 plus 4 times 1. That's 8. I'm going to always divide by 2. I'm going to get 4 pair. The Lewis dot structure is right here. And again, if you need a refresher on that, then you most certainly need to be watching my covalent bonding worksheet number 1, where I go over the details of that one specifically. That is the Lewis dot structure here, and that is a tetrahedral geometry, and that is 109.5 bond angle. It is nonpolar, and in my class, you would have to build that model, and you're going to get my autograph. All right. So without further ado, let's continue on. Hydrogen. Hydrogen is a diatomic. And di is the prefix for the number 2. And then atomic is atom. So atom. So there are 2 atoms within this one molecule, and that's what we're looking for here. So the formula for hydrogen is none other than just H2. By the way, if you want to know, hydrogen is a gas. Not that that is necessary on this one here. So the number of valence electrons in hydrogen is the following. So we're going to pull out our periodic table, and hydrogen has 1 valence electron. Perfect. So that's 1 valence electron, and there are 2 atoms of hydrogen. So I'm going to multiply that by 2. I'm going to get 2, and then I'm going to divide that by 2, and I'm going to get 1 pair. So I'm going to use that 1 pair. All right. Pretty simple there so far, hopefully. Okay. And then what we're going to do is we are going to look on this lower half of this worksheet here. We have summed up the total number of valence electrons. There's no ownership to electrons. Follow the rules below for placement. We don't have to do A because there's no a positive or negative charge. We're going to determine the central atom, that is the least electronegative element. However, it cannot be hydrogen. Well, here's the funny thing. There are only two atoms. One of them is hydrogen. The other one is hydrogen. So I'm going to have hydrogen. I'm going to have a hydrogen, just like that. And then we're going to place the electron pairs. We have one pair according to the set of rules. And that set of rules is as follow. Place those atoms around 3, 6, 9, and 12 o'clock. Well, we don't have to do that either because there's no other atom. So we're doing 3A. Place a pair of electrons between the central atom, A, and the surrounding atoms. There is no central atom. We have one pair, and so we're going to draw this single line there like that. Now, just so that you know, here's what we're doing here. Okay, so I am doing this mentally in my head. I'm going to do this in pencil so that I can erase this in just a moment, but I'm going to circle each atom at a time. And hydrogen follows what's called the duet rule, which is 2 electrons. So that has each line represents 2 electrons. So that's 2 electrons for this right-hand hydrogen. This left-hand hydrogen, it has 2 electrons. That's also a duet. So the duet rule has been satisfied. Again, that information is erased. That is done in my head. All right. Perfect. That is the Lewis dot structure for hydrogen. Okay. Now what we need to do is figure out the molecular shape or molecular geometry. And here's the kind of the funny thing. In order to figure that out, what we're going to do is we're going to go over to here, okay, and this top section of this worksheet, okay, and there's no central atom. In order for me to have a shape, I need at least 3 atoms in order for me to have a shape. So this is classified as no shape. No shape. Therefore, there's no bond angle, so we're not going to do that. We can answer the question of polarity, but we do first, we need to make the model. And here's the model for hydrogen. Okay, so hopefully you can see that pretty well. Let's just give a different background on that so that you can see that more clearly. There is hydrogen. There's one hydrogen atom. There's another hydrogen atom. That gray thing right in between are the shared electrons between the two. So that is hydrogen. Well, both sides are the same. This is a symmetrical molecule. So being that it's symmetrical and the same, that means it is non-polar. And we just built the model. Perfect. All right, that was super easy. Easy peasy, not too bad at all. All right, so let's continue on with the next one. Okay, the next one is fluorine. And fluorine is also a diatomic. You're going to see that continuous theme throughout this worksheet here. Fluorine is F2. It is also a gas, not that that's necessary on this worksheet here. It is the most reactive non-metal element here. Okay, fluorine, we got to figure out the valence electrons in fluorine. And there is fluorine. There are 7 valence electrons in fluorine. So that's 7 valence electrons in fluorine. There are 2 fluorines. So that's 14 total electrons. We're going to divide by 2, as always, and we're going to get 7 pairs. Perfect. All right, we're going to draw a fluorine atom and another fluorine atom, and then we're going to follow the rules of electron placement. And so there's no central atom. There's no other atom for me to look at. So we're just going to go place a pair of electrons between the central atom and the surrounding atoms. So bingo, done that. That's one of my 7 pair. If electron pairs remain, place a pair of electrons on the surrounding outside atoms as lone pairs. Excuse me. So that's one pair, two, three, four, five, six, and seven. Awesome. That looks fantastic. So what you should see there is we're going to circle this right here, this atom right here on the right-hand side of fluorine. We got one, two, three, four pair. Fluorine obeys the octet rule. That four pair is 8 electrons. This left-hand fluorine, one, two, three, four electron pairs. That's 8 electrons. That's an octet. Both fluorines are satisfying the octet rule. I'm going to erase that here because that really doesn't belong. All right, so now what we need to do is we need to figure out what the shape is. And again, the shape, we need 3 atoms in order to have a shape. So there's no shape. And there's no bond angle for this either. This is symmetrical, or these two things are the same. And if it is symmetrical and the two things are the same, it is non-polar. And we need to make the model for this. And I have made the model already here for you. Check this out. So these two green things are representing each fluorine atom. This gray thing is representing the bond in between. And then these pink items here are representing the lone pairs of electrons on the fluorine. Okay. And those would be those red dots that you see. Okay. Hopefully that is making sense to you. Now, depending on the pond, the model kit of which you have, you might not have these cute little pink things here, of which I have. You might have something else. So let me show you something else that you might have. And then these would work as lone pairs. So these little paddles that we have are viewed as lone pairs as well. Okay, and so I'll just put these on here, and this will just give you another representation of this molecule. You know, if this molecule will really work in here, then these lone pairs would be counter to one another, right? They would not be in line, in sync like that. They would be alternating just like that if this were a real molecule, okay? Of which fluorine is. So that's kind of what that looks like. These tannish things here are the lone pairs of electrons here. All right, perfect. We're going to pull that one off to the side, and we have most certainly done that one. We're going to do the next one there, and that is oxygen, and that is also diatomic. And oxygen is O2. Oxygen, molecular oxygen, is also a gas. We need to figure out the number of valence electrons in oxygen, and oxygen is right here. So there are 6 valence electrons in oxygen. So that is 6. We're going to multiply that by 2. I'm going to get 12. I'm going to divide this by 2 as always, and I'm going to get 6 pairs. I'm going to have an oxygen here and an oxygen here just like that. All right, perfect. Now what we're going to do is we are going to follow the sets of rules of placements of electrons, and that is the following. We got 6 pairs. First, bonding electrons between the central atom and the outside atom. We're going to put that right there like that. Then what we're going to do is we're going to place lone pairs of electrons on the outside atoms. So, well, we have 6 pairs. We've used 1, so we have 5 left. I'm going to do this in pencil, and then you're going to see that I'll erase some of these and move some of them and not erase others. Okay? So 1, 2, 3, 4, 5, and 6. All right, so now what we're going to do is we're going to circle this right-hand oxygen, and we're going to ask ourselves, does it have an octet? That's 2, 4, 6, 8. That has an octet, so that's good. Now we're going to circle this left-hand oxygen. We're going to count up the number of electrons around it. That's 2, 4, 6. That's 1, 2, 3 pair. 6 is not an octet. So now what we have is a problem. Oxygen is in period 2 on the periodic table, so let's just verify that. This is period 2, period 2. Carbon, nitrogen, oxygen, and fluorine must obey the octet rule. Oxygen must obey the octet rule. So we need to get an octet on this oxygen. Do I have any more pairs of electrons? I only have 6 pair to play with. That is 1, 2, 3, 4, 5, and 6 pairs that I can play with. That's it. So now what I'm left with is somewhat of a dilemma. And so that is, in order to satisfy the octet rule, multiple bonds, double or triple, may be necessary by sharing electrons. So in this case, sharing is caring. So what we're going to do is we're going to take our pencil here and our pencil eraser, and that is erase a pair of electrons that are on this right hand. And it doesn't matter which pair you remove. But we are going to keep them within the circle of which is already here. And we're going to place them within the circle, but share them with the other atom. Now that is a double bond. Now I have in this right-hand oxygen, do I have an octet still? That's 2, 4, 6, and 8. Yes, I do. On the left-hand oxygen, I didn't have 8 electrons. I had 6 electrons. So let's see if I have 8 now. That's 2, 4, 6, 8. I do, most certainly. So that's fantastic. So now what we're going to do is we're going to erase all this and then write it down like it looks. Okay, let's make sure this is correct. So this is going to be a double bond. We're going to have 2 sets of lone pairs of electrons on that right-hand oxygen and 2 sets of lone pairs of electrons on that left-hand oxygen. Perfect. That's exactly what it looks like. That is a beautiful thing. Again, I need 3 atoms in order to have a shape. So this is no shape. If no shape, then there's no bond angle. These 2 things are the same on both sides, so it's symmetrical. And that means it's nonpolar. And we're going to build ourselves a model here in just a second. So this is what we're going to do. We're going to build ourselves a model, and let's see what we get for this model. So in this model, I cannot use these short, stubby things like what I've used before. So what we're going to do is we're going to use these long, bendy things. Okay. And we need some lone pairs of electrons on this. So that's what we need to use. And so here we go. Here's our 2 sets of lone pairs of electrons on the outer edge of each oxygen. Now, that looks perfect. So what do I have here? I have my double bond in the middle here. This is a double bond. I got my 2 oxygens, and I've got my 4 lone pairs of electrons, 2 on each oxygen. All right, that is my model for this. And you can see that it's symmetrical and most certainly nonpolar. That's a beautiful thing. Hey, we got one more to do. This is going to be a very short video relative to the previous one. The next one might be a little bit longer. The next one is nitrogen. That's also diatomic. And that is N2. That is the most abundant gas in our atmosphere. That's an amazing thing, isn't it? Okay, it's non-reactive gas, and we keep on ingesting that gas all the time, every day, every minute, every hour. Okay, here we go. N2. So we're going to find out the number of valence electrons in nitrogen. Nitrogen is also in period 2, and it has 5 valence electrons. So that's 5 valence electrons. There are 2 of them. That's a total of 10. Of course, just like always, we're going to divide by 2, and we're going to get 5 pair of electrons. We're going to have a nitrogen and then the second nitrogen. And again, like I did on the previous one, we're going to do this in pencil. So the first rule is to place a pair of electrons between the central and the outside element. There is no outside element. There is no central element. So I just have to place a pair between these 2. Then we're going to place electron as non-bonding lone pairs of electrons on the outside atoms. So I have 5 pairs. I've used up 1. I have 4 left. So that's 1, 2, 3, and 4, just like that. So let's just verify and count 5 pairs. That's 1, 2, 3, 4, and 5 pair. Now what we're going to do is we're going to circle this right-hand nitrogen, and nitrogen obeys the octet rule. Does this nitrogen on the right-hand side that I've circled have 8 electrons around it? Well, let's check here. That's 2, 4, 6, 8. It most certainly does. So I'm going to circle this left-hand oxygen and ask the same question. Nitrogen follows the octet rule. Does this nitrogen have 8 electrons around it? Well, it has 2, 4. That's 2 pair of 4 electrons total. It most certainly doesn't. Darn, what am I to do? Well, do you remember what we did with the oxygen molecule just above this? We're going to do something similar here. So what we're going to do is sharing is caring. So in order to satisfy the octet rule, I'm going to make multiple bonds. So what we're going to do is we're going to take a pair of electrons away from the nitrogen on the right, and we're going to put them in the middle. I need to keep them with the nitrogen on the right because it already has an octet and I don't want to remove them, right? So if I didn't put them in the middle like I just did, let's just pretend I didn't do that. Let's say I kept that single bond there and just gave them to that left-hand nitrogen. Then this right-hand nitrogen has 2, 4, 6 electrons. The left-hand nitrogen has 2, 4, 6 electrons. I don't even have an octet on either. So that is not the right path to follow here. The correct path to follow is the following. I'm going to take this pair of electrons and I'm going to share it in the middle. I still maintain the octet on the right-hand nitrogen, and I'll prove that to you for you right now. And that's 2, 4, 6, and 8 electrons around it. Now, I used to have 4 electrons or 2 pair on this left-hand nitrogen. Now I have 1, 2, 3 pair and 6 electrons. So I'm getting closer to my octet, but I'm not quite there. So what I need to do is still sharing is caring. Let's continue the same process here. And we're going to put another pair right there in the middle. Okay, and now I'm going to look at my right-hand nitrogen. It has 2, 4, 6, and 8 electrons. The left-hand nitrogen has 2, 4, 6, and 8 electrons. I've satisfied the octet rule for both. Perfect. Now, that is a triple bond. So I'm going to clean this up. I'm going to erase all this here and then clean it up and make it look nice and pretty, like what it should look like here. So let's get rid of that, and we'll do this in red so it's nice and clear. So there is actually a triple bond in between the 2 nitrogens, and then there's a lone pair of electrons on each nitrogen like this. Now what we're going to do is we're going to build the model for this here, just like what we were doing before on other ones. We're going to use those same kinds of bonds that we used for the oxygen, right? So here's our oxygen, we have that one, and here is our nitrogen. Hopefully that looks good to you so far. All right, fantastic. So let's remove the oxygen since we're really focused on the nitrogen here at this moment in time. And you should see that these gray here, there's 1, 2, and 3. That's a triple bond. And then there's the lone pair of electrons opposite of it like that. What's the shape of this? You need 3 atoms in order to have a shape. So there's actually no shape on this. Okay, the bond angle is none. This is symmetrical. Symmetrical. That means it's non-polar. And yes, we made the model for that, as you can clearly see right there. All right, so excuse me. You should see one other thing I'm going to mention here, and we're going to use the models here to answer this question here. So this is kind of like an addition to the whole thing. You should see that the hydrogen in the upper left, this is the hydrogen, then the oxygen, and then the nitrogen. You should see that as you get to go from a single bond, a double bond, to a triple bond, you should see that the atoms get closer together as the bond increases. So this is called a bond order. This is a bond order of 1 as a single bond. This is a bond order of 2 with a double bond, and a bond order of 3 with a triple bond. Triple bond, the atoms are closer together. The double bond, they're farther apart, and the single bond, they're yet the furthest apart. That's pretty nifty. That means it costs more energy to break this triple bond than a double bond, and consequently the least amount of energy to break that single bond. Something very important in later concepts of chemistry. I just thought I'd throw that out there for you. By the way, this is the covalent bonding worksheet number 2. And I forgot to give a note to our sponsor, so I apologize for that. Today's sponsor of today's video is none other than the awesome, the one, the only, the crazy hat chemist. That is me. So I'm looking for sponsorship. So, maybe you want to shoot me something and see if you want to sponsor me. That would be fantastic. Give me a like, give me a subscribe. I love you. I'm going to see you next time. We're going to have a covalent bonding worksheet number 3, I'm sure, in the very near future. So please give it a like, subscribe, and thank you very much for watching. Appreciate it. I'll see you next time. Bye for now.